Okay, today we're going to be finishing with Newton's third law, and we're going to talk about normal force, because it's so much better than those strange forces. So let's finish off with the third law. The third law says that every action has an equal and opposite reaction, and by action we usually are referring to force. So basically, if you are so unlucky to hit the wall because you forget that walls can hurt your hand if you punch them. Oops, whatever. What's going to happen is you apply a force to there, and the wall is going to apply a force right back at you, and believe me, the wall can take a force much better than your bones can. But obviously, when some people get mad, they like to forget that. Natural selection, I suppose. So now we are going to use this and apply it to something called normal force. Normal force is the reaction force from a surface. Okay? And here's one thing to help you out. This is going to be always perpendicular. Are you okay with that? Do you remember that symbol? Always perpendicular to the surface. Alright, let's use an example. Here's a chair. Ooh, we'll even make it in 3D. How about that? Now here's you in the chair because you're not in school right now. And then what's happening is you have gravity on you. Can you feel it? Anyways, gravity is going to be pulling you down, so I'm going to put a G there. Now, obviously, you are not going to fall down to the center of the earth, at least not at this particular instant. So you are not falling down because the chair is going to be holding you up. The chair is going to apply a normal force. So we usually do Fn. We usually call this Fg too, because it's a force technically. So these two forces are going to be opposite and equal because they are balancing each other out. So remember adding vectors together. What we just made right here is called a free body diagram. It's just a fancy word, fancy name for just drawing the forces on an object. Okay, there are two forces on you sitting in a chair. Force number one is gravity grabbing you down. Force number two is the normal force that pushes you up. Now, because you're not moving, your forces should add up to 0 because they're opposite and equal as well. Alright, so that's what a free body diagram is. We're going to be drawing tons of them again in this class. Alright, so let's talk about a normal force on an incline. Here's an incline. Alright, there's some angle there, doesn't matter. So here's a box. The box is on a hill. Now let's say we want to draw the forces. We want to draw a free body diagram. Okay? So what's going to happen? There's going to be a force of gravity that goes down just like there. Now there is also going to be a force normal. The force normal is not going to be going straight up anymore because the force normal is always perpendicular to the surface. So the force normal is going to be something like that. The force normal will always be a little less. Well, always is a strong word, but in this situation it'll be a little less. Because why? Because what happens is if we wanted to figure out values on this, we have to break these apart just like before whenever we have component vectors like this, whenever we have diagonal vectors, we have to break them into components. So we are actually going to do something a little different. Instead of breaking apart the diagonal force normal, we are going to break apart the force gravity. The reason is because we're going to adjust our frame of reference to the slope. We don't care about absolute up and down. We care about the angled version of this. So we are going to break the gravity apart into two pieces. All right, this is a difficult triangle to visualize. Now, this guy right here is the force of gravity that is perpendicular to the surface. Okay, so if you're standing on a hill, this is how much gravity is pulling you into the hill, like how much weight you feel into the ground. Okay, this guy right here is the force of gravity that is parallel to the surface. This is the amount of gravity that's pulling you down the hill, okay, making you roll, okay. So let's talk about how to calculate these. Remember, this is going to be at some angle, we'll call it theta, right? Now, it's difficult to see, but these two triangles are going to be similar triangles, right? Because they're both 90 degrees. Now, this one has a vertical piece, this one has a horizontal piece. If you rotate it around, what you're going to find out is the theta is also going to be right there, okay? If you kind of flip it, I can't really show you because I only have one screen here, but you know, you can kind of rotate it around. Anyways, so what we're going to find out is the perpendicular force of gravity is going to equal the original force of gravity times your cosine theta, and likewise it's going to be this guy with the sine theta. Okay, so what's your force normal going to equal? Your force normal is going to counteract the perpendicular gravity, so this is going to equal your Fg cosine theta. Alright, the reason why it's going to do it like that and it's not going to use here is because it is pointed in the opposite way. So your force normal is counteracting its opposite force, okay? This one is not its opposite. This one is pointed down the hill. So, if this box were, if it were frictionless, and we're saying it is, we're not talking about friction until next week, what's going to happen is it's going to slide down the hill with this force, okay? This is what's going to be accelerating it. So often this is called the net force, F net. I like to just use F plane for force net because it's one less subscript. But anyways, so that's how that's going to work. Let's do a practice. What is the net force down a 30-degree slope that is frictionless? Oops, I'm sorry, I didn't want net force. I want acceleration. But let's do it. So let's draw a picture. Pictures are wonderful. Here's a 30-degree angle. Here's my box. My box has a mass of m because I didn't tell it to you. Spoiler alert, you don't need it. Now, let's draw all the forces here. There's one force. This is going to be your force of gravity. Your force of gravity is m times g, right? Because F is equal to ma. M is your mass. A is your acceleration. What's your acceleration? Acceleration is gravity. All right. This guy right here is going to be your force normal. We'll figure that out later. But what we have to do now is figure out the components of the gravity. So this is going to be 30 degrees. So if this is mg, that means this is going to be mg sine 30, which is just half, right? mg over 2. And this guy is going to be mg cosine 30, which is going to be root 3 over 2 mg. Alright, so far so good. So things we can figure out, we know that the force normal is going to be root 3 over 2 mg, right? Ta-da. We don't actually care about that quite because the net force, if we added these together, and the is going to be pointed down the hill, and this is the only force that does not cancel out. So this is our net force, right? Whenever something doesn't cancel out, it's part of the net force. So how do I figure out the acceleration then? Well, F is equal to ma. This formula only works when you have the net force, okay? Because otherwise you're not accelerating because it's not the net force. So we're going to have mg over 2 is equal to m times a. Do you see it? Hopefully. The m's cancel out. So acceleration is going to be g over 2, or 4.9 meters per second squared. Ta-da! Hey, and that's it. So something you should be aware of is that mass cancels out for a lot of these, but that's how you can figure out acceleration down a slope. That is a big thing, and we are going to add on to that tomorrow. But you should also think that you can combine this with all your motion stuff from the past. So I could tell you how long does it take to slide down a 100-meter slope like that. And you could figure that out because you know the acceleration, and then you've used that to figure out the time or whatever. Okay. Hey, so that's that. I know that was fun stuff. I'm sure you'll have plenty of fun to practice it.